In this section, we will study Boolean ring and algebra. Okay, for first, let us define Boolean algebra. Okay, we call S to be a Boolean ring. If S is a ring and every element in S is an idempotent. Okay, and we call this to be a Boolean algebra. If first S and is a semi-lattice and 0 is an element of S and the prime is a unary operation on S such that A and B prime is 0 if and only if A and B is A. And A and B is A means A smaller than or equal to B. Here, in the following, I will call A smaller than or equal to, simplify by smaller than. Okay, now let's see the lemma. If S is a Boolean algebra, then A2 prime is A. Okay, to prove this, we should prove this on two different parts. First is A2 prime smaller than A and A smaller than A2 prime. Okay, to start with, A2 prime smaller than A. If we want to get this result, by here, we should get A prime and A2 A2 prime and A prime is 0. And change the set A prime and A2 prime, and we written by this is 0, right? And then we should get A prime and smaller than A prime. Actually, A prime must smaller than A prime, right? So we can get A2 prime smaller than A. Okay, let's see. We writing it very carefully. A prime smaller than A prime. So A prime and A prime prime, that is A2 prime, is 0. So A prime, A2 prime and A prime is 0. A2 prime smaller than A. Okay. And the second, we should prove A smaller than A2 prime. To get this one, we should get A and A2 prime is 0. Okay, that is A and A3 prime, right? A3 prime is 0. Here, how about if suppose A3 prime is A prime, then we change to A and A prime is 0. Then A smaller than A. Actually, A smaller than A is true, right? So we remain to prove A3 prime is A prime. Okay? We need to show A3 prime equal to A prime. Also, we use two parts. A3 prime smaller than A prime and A prime smaller than A3 prime. Okay, to see first, A3 prime smaller than A prime. This is very easy to get by 1, right? Because we change A prime by A to A, then we can get this result, right? And the second, we should prove A prime smaller than A3 prime. Okay, if we want to have this result, we should have A prime and A3 prime prime. That is A4 prime, right? A4 prime is 0. Okay, let's change the set. A4 prime and A prime is 0. So A4 prime smaller than A. Is this true? Actually, this is true because A2 prime smaller than A, right? So A4 prime smaller than A2 prime and A2 prime smaller than A. So by the transitivity, we can get this one. Okay, let's writing this carefully. By 1, we can get A4 prime smaller than A2 prime and A2 prime smaller than A. So we get A4 prime smaller than A. Then A4 prime and A prime is 0. Then change the set A prime and A4 prime, that is A3 prime prime, is 0. Then we get A prime smaller than A3 prime. Okay. Then by these two, we can get A prime equal to A3 prime. So let's back from here. Because A smaller than A, so A and A prime is 0. And because A prime is A3 prime, so we change A prime to be A3 prime. And here A3 prime we written as A2 prime, prime is 0, right? So we can get A smaller than A2 prime. Okay, we prove this. Okay, let's erase some other things. Okay. Okay, actually we get this. This is the final result. And let's see the following propositions. Okay, let's say S is a Boolean algebra. Then S can be a complicated distributive lattice by defining the equations A or B equal to A prime and B prime prime, and the complement of 0 is 1, and the converse is true. Okay, let's prove this. Okay. First, suppose S0 prime and to be a Boolean algebra. Then we want to show this is a completed distributive lattice. So we should prove first this is a lattice, right? Lattice means lattice. Lattice means we should to show A or B smaller than C if and only if A smaller than C and B smaller than C. Okay. For every element A, B, C in S, we suppose A or B smaller than C. Then, by the definition, we have A or B and C prime is 0. And by these equations, we have A prime and B prime and C prime is 0. Let's change the situation. C prime and A prime and B prime is 0. So we can get C prime smaller than A prime and B prime. So we can get C prime smaller than A prime and C prime smaller than B prime. Okay. Then we have C prime smaller than A and C prime smaller than B. Oh, sorry. Here must C prime and A is 0 and C prime and B is 0. So we change this B and C prime is 0. Then we get A smaller than C and B smaller than C. Okay, we get this result. So S is a lattice. And second, we should prove this is distributive. Okay. That means we need to show A and B or C equal to A and B or A and C. That means if A and B or C smaller than X, if and only if A and B smaller than C and A and C smaller than C. Okay. First, also for A, B, C, and X in S, A and B or C smaller than X if and only if A and B or C X prime is 0. So this means A and X prime. And here B or C we change it as B prime and C prime is 0. So we can get A and X prime smaller than A or B prime and C prime. Okay, that means A and X prime smaller than B prime and A and A and X prime smaller than C prime. Okay, this means A and X prime and B prime is 0. A and X prime, here and B. This and C is 0. And also we change the situation. Let S to be the last one. So we can get A and B smaller than X and A and C smaller than X. So we complete this proving. And third is we need to show this is completed. Okay, to show this is completed, that means every element exists a complement. Complement. Okay, so how to prove this is complement? We should found this complement. Okay, because a smaller than a, then we can get a and a prime is 0. This is, and a or a prime equal to a prime and a2 prime, right? And because in here Boolean algebra has a2 prime equal to a, so we can get a prime and a. And the inside is 0, so 0, the complement of 0 is 1, right? So this is 1. So from these two equations, we can say every element in S have complement, okay? And the last one we should to show every element in S is between 0 and 1, okay? That means we need to show first A bigger than 0 and smaller than 1. Okay, to show this, we should have A and 0 and A prime is 0. Actually, 0 and everything is 0, right? And here, we need to show A and 1 prime is 0. Actually, this is A and 0 is 0, right? So this two is very easy to prove. Okay, then S is completely the distributive lattice. Okay, and next we will prove the inverse. If S is a completed distributive lattice, S is completed distributive lattice, and we want to show this is a Boolean algebra. That means we should prove three things. First is S and is a semi-lattice. Okay, this is trivial because S is a lattice. Clear. And 0 is an element of S. Also, this is clear by the definition. And the third one, we need to show the prime. We need to show A or B prime is 0 if and only if, oh sorry, here, A and B prime is 0 if and only if A smaller than B. Or how to say A and B is A. Okay, we need to show this. For the first part, suppose A and B prime is 0, and we want to prove here. So begin to the A. A is A and 1, right? And the 1 can be written as B or B prime. So distribute it A and B or A and B prime. Okay, this one should be 0. So we have A and B. So A equal to A and B. And the other side, we need to we suppose A is equal to A and B. We need to show this one. Okay, so begin with here A and B prime, because A is equal to A and B, so here A and B prime. Okay. By the associative law, we have A and B prime, right? B and B prime is 0, so here A and 0. A and 0 is 0, so we complete the third one. And moreover, if S is this one, then it must satisfy these equations. Okay, let's see. The first equation is okay, A or B equal to A prime and B prime prime. To show this, that means the complement of A prime and B prime is A or B, right? So to prove these two are complement, we need two things. First is A or B, and A prime and B prime is 0. We need to prove this is 0 and A or B, or A prime and B prime is 1. We need to show this is 1. Okay. From here, oh, sorry. Here we use the distributive law. A and A prime and B prime, or B and A prime and B prime. Okay, let's see. A prime 0, B prime 0. So 0 or 0 is 0. And here A or B or A prime, A or B or B prime. Okay, A and A prime, B and B prime is 1, right? So 1 or B, 1. 1 or A, 1. So this is 1. Okay, so these equations can be true. And nothing's here. We should prove it here. The complement of 0 is 1. That means we should prove first, just like 1 and 0 is 0. 1 or 0 is 1. Actually, this two are true, right? So because 1 and 0 is 0 and 1 or 0 is 1, so the complement of 0 is 1. Okay, so we complete these propositions. That means the Boolean algebra it can be completed distributive lattice, and the complement. Sorry, I always use the wrong words here. Not completed, complemented. Okay. Okay. So let's see the following corollary. Okay. If S is Boolean algebra, then this is Boolean algebra 2. Okay, and this is very easy to prove, and we call each of these to be dual of each other. Okay, then let's see the following propositions. That means S0 prime dot Boolean algebra can be turned into a ring. Boolean ring by defining these equations. First is this one, and A plus B. A plus B equal to A B prime or B A prime. And where A or B is A prime, B prime. Okay, and prime as usual. And any Boolean ring can be regarded as Boolean algebra. But here equations change to A prime is 1 minus A. Okay, so let's prove this. First, we suppose S is a Boolean algebra. And we want to prove this is a Boolean ring. That is means we should first prove this is a ring, and then every element is idempotent, okay? And to prove this is a ring, we need to show first under the plus operation, S can be a abelian group, and under the multiply operation, S can be a semigroup, and S satisfy the distributive law. Okay, let's see. First, I want to show S under plus is abelian group. Okay, to show this is abelian group, first is it satisfy associative law. Okay, that means we need to show here if A plus B plus C equal to A plus B plus C, right? Okay. Okay, here we notice that A or B prime equal to A prime B prime, right? So we have A prime and B prime equal to A prime B prime. So that means A B is equal to A and B prime, right? It will be more simpler. Okay, let's write down. Okay, because A or B equal to A prime B prime prime. So A prime and B prime equal to A prime B prime. So equal to A and B. Okay, and from here A plus B. So A plus B, A B prime or B A prime. This is equal to A and B prime or B and A prime. Okay, by the distributive law, we say this is a intern. A and B prime or B and A and B prime or A prime. So it will get A and B or B prime and B. Oh, sorry. Here. A or B. A or B and B prime or B. Okay, and here A or A prime and B prime or A prime. Okay, here this is 1, 1. So here A or B and B prime or A prime. Okay, so A plus B not only can be written as this form, but also can be written as this form. Okay, these two forms was very important. Okay, let's see. Want to prove the associative law. A plus B and plus C. That means A B prime. Actually, we use here A plus B and C prime or A plus B and C. Oh, sorry. Here it must C and wait. C and A plus B prime. Okay, then A plus B is A and B prime or B and A prime and C prime or here A yeah copy. Hmm? Here. Okay, prime right and C. Okay, then let's see. It can be written as distribute A and B prime and C prime here, or B and A prime and C prime. Okay, or A and B prime and C, or B and A prime and C. Okay. Okay, let's change the situation to be C and B prime and A prime, or C prime and B and A prime, or C prime and B prime and A, or C and B and A. Okay, let's see. Here, mm, yeah, I'm sorry, here is something wrong. Here, A prime or B prime, or A prime and here is C and A prime and B, here A and B. Okay, so we get this. Actually, this is C plus A plus B. So A plus B plus C. Okay, and second, the identity. That means for every element in S, the identity is 0. We need to show S plus 0 is S. Oh, sorry. Here. S 0 prime or S prime 0. S 0 prime or 0 S prime. That means S and 0 prime or 0 and S prime. Okay, let's see. This is 1. This is 0. S and 1 is S. So this is S. And we also need to show 0 plus S is S. Also, here just change the S and the 0. 0 S prime, S 0 prime. Okay, 0 and S prime, or S and 0 prime. Okay, this is 1 S and 1 S, and there is 0, so also this is 0, or this is S. So the identity exists is 0. And inverse. Element has inverse. Actually, the inverse is 1 plus 1 minus A, right? Because a prime equal to 1 plus a. So minus a is a prime minus 1, right? And we want to show a plus minus a is 0. And change the minus a to be here. A plus a minus 1, right? A plus a prime minus 1. Okay. Here, a plus a prime means a2 prime or a prime a prime. Okay, minus 1. Okay, this is because this is Boolean algebra, so a2 prime is a prime is a. So here a or a prime or a prime and a prime minus 1. Okay, here a prime a or a prime is 1. So 1 minus 1 is 1. Okay, so 1 minus 1 is 0. And on the other side, minus a plus a, also we can get 0. So minus a is inverse of a, right? Under plus operation. And last commutative. This commutative is very easy. A plus b equal to b plus a. We want to show this. Okay. For a plus b means a b prime or b a prime. This is a and b prime or b and a prime. Okay, let's change the situation. Can be b a sorry, b and a prime or a and b prime. Okay, actually this is b plus a. So the commutative law is true. And so this show S plus is semi-group. Sorry, opinion group. And let's show S under product operation is a semi-group. Okay, to show this is a semi-group, that is, first we should show the associative law. A times B times C equal to A times B times C, right? We should show this. Okay, let's see. By here, AB means A and B. So A and B and C. This can be written as this. So A and B and C, right? So A, B, C. So, and that means S under this production is a semi-group. Okay, the third one is to prove the distributive law. That means for element ABC, if A times B plus C, it is equal to, we want to show this is equal to AB plus AC, right? Okay, let's see. A and B and C prime or C and B prime. Okay. Then distribute A and B and C prime, or A and C and B prime. Okay, and on the other side we see AB plus AC. Oh, sorry. Okay, this is A and B plus A and C. This is more complicated. A first, A and B and A and C prime, or A and B and sorry, A and C and A and B prime. Okay, A and B and A prime, or C prime, or A and C and A prime or B prime. Okay, let's distribute it. A and B and A prime, or A and B and C prime, or A and C and A prime, or A and C and B prime. Okay, then A and A prime 0. A and A prime 0. So here remains A and B and C prime, or A and C, A and B prime and C. Okay, actually here is the same equations. So we get from here, we can get A times B plus C equal to A B plus AC. Okay, and on the other side, A plus B times C equal to AC plus BC, as this is true by the upper result, right? Okay, so then we can say abelian ring, abelian group, semigroup, and distributive means S should be Boolean group ring. Okay, and second, we want to say if S is a Boolean ring, then S is a Boolean algebra. Okay, to prove S is a Boolean algebra, we should prove first semi-lattice, right? One S and is a semi-lattice. Actually, because the proposition 1 here, proposition 2 here, without, okay, because a semi-group can be a semi-lattice. Variation 2. This is a semi-group, right? Then this is a semi-lattice. Okay, so 2, 0 is an element in S. This is clear by the definition. And the third one, we should prove A or B prime, A and B prime is 0 if and only if A and B is A. Okay, to show this, let's see. If A and B is 0 if and only if A 1 minus B, because B prime equal to 1 minus B, right, is 0. And then A equal to AB. Okay, that means A and B. So these three conditions makes S is a Binetian algebra. Okay, so let's see the following definitions. Also here, S under this relation is an ordered set. And here T is a subset. Sorry. T is a subset of S. And we call an element in T to be a upper bounded least upper bound if for every element T in T, S bigger than T, then this is upper bound. And we call S is a least upper bound. Actually, we usually use sub T if for all upper bound S prime in T, S bigger than S prime. Okay. And we call S under this relation is a complete lattice. Okay, here not complement is complete if every subset of S has an inf and a sub. Okay, let's see. Here I forget to say if a subset of other sets have sub, then the sub is unique. If exist, then unique. because if S and S prime is the sub of T, then because S smaller than S prime is smaller than S because the sub deflation, so we have S equal to S prime, okay? And the lower bound define the dually. Lower bound, here lower bound, right? Or change the set, S smaller than T. Here, lower bound are inf T. Here, S smaller than S prime. Here, lower bound. Okay. Here, and notice that the sub of T equal to the inf of this set. Okay. And we call S under this relation to be well-ordered. If every non-empty subset of S has a least element. Okay. And we call a Abelian ring is a Abelian algebra is called complete if it is complete that is okay. Here I have a note here. By a closure operation on a complete lattice is understood. A mapping S goes to SC of S into S such that A smaller than AC and AC smaller than AC and A smaller than B if and only if AC smaller than BC. Okay, let's see another definitions. Closed. We say this is a complete lattice and an element in S is called closed if AC smaller than A. Okay, so let's see the propositions. This section, the last propositions. Okay. 5. Oh, sorry, 4. This is 4. Giving a closure operation on a complete lattice, then the inf of any set of closed element is again closed. Here the closed element forms another complete lattice. And conversely, any subset of a complete lattice which is closed under the operation inf can be obtained in this way. Okay, let's prove this. First, to the beginning, we suppose S under this relation is a complete lattice, and with the closure operation C. Okay, first, let X to be a set of closed element A equal to inf
and S belongs to X if and only if AC belongs to X. Because x3 or x is smaller than